Alright, let's dive straight into the fascinating world of energy-based transformers. This paper tackles a big question. Can we make AI models that truly think like us, not just react instantly, but deliberate, analyze, and reason, all learned from scratch without needing tons of specific training data? So, we humans have this amazing ability to think in two ways. There's System 1, your gut feeling, fast, automatic, like recognizing a face or catching a ball. Then there's System 2, the slow, thoughtful process, like solving complex math, planning a trip, or writing code. It's deliberate, analytical, and takes effort. Current AI models, especially the big language models, are fantastic at System 1 tasks. They're quick learners, pattern recognizers. But when it comes to System 2 thinking, the really tricky stuff, they often stumble. We've seen attempts to boost AI reasoning. Some use reinforcement learning, like teaching a model with rewards, which works great for math problems where you know the answer is right or wrong. But these models often don't generalize well to other tasks like writing and might just be getting better at things they already knew. Diffusion models, popular for image generation, can do iterative steps, but they usually need an outside judge to tell them if they're doing a good job. Recurrent neural networks, or RNNs, can also loop through information, but standard ones often forget what came before, and even advanced ones lack a built-in way to verify their predictions. So, the big question this paper asks is, can we build AI that learns to think deeply, like System 2, purely by learning from data, without needing special supervision or being limited to specific types of problems? To figure out how to build this thinking AI, the authors break down what makes human System 2 thinking so effective. They identify 3 key ingredients, or facets. First, dynamic allocation of computation. Think about it. You don't spend the same amount of mental energy deciding what to eat versus figuring out a complex engineering problem. Humans naturally allocate more effort when needed. Second, modeling uncertainty. We don't just make decisions, we weigh how confident we are. I'm pretty sure that's a cat, versus, maybe it's a cat, maybe a dog. Especially in continuous spaces like vision, where things aren't discrete categories, expressing uncertainty is crucial. Third, verification of predictions. Can you check if your current thought makes sense? Can you stop thinking once you're satisfied? This is core to human cognition. Now, look at the table. Traditional feed-forward transformers and RNNs? They're stuck. They compute a fixed amount per prediction. Diffusion models can add steps, but they don't inherently know how to verify or estimate uncertainty. The proposed energy-based transformers aim to hit all 3 targets: dynamically adjust computation, model uncertainty, and explicitly verify predictions. That's the holy grail they're aiming for. So, how do they actually build this thinking machine? The core idea is beautifully simple yet powerful. Instead of directly learning to predict, they learn to verify. Imagine you have a context, say, the quick brown fox jumps over the lazy dog. And you have a candidate prediction, maybe the first few words, the quick brown. An EBM learns a function, an energy function, let's call it E theta. This function takes the context and the prediction and spits out a single number, the energy. If the prediction fits perfectly with the context, the energy is low. If it's nonsense, the energy is high. It's like a compatibility score. To make a prediction, you start with a random guess, maybe just noise. Then, you ask the EBM, how compatible is this random guess with the context? It gives you an energy score. You then nudge your guess slightly in the direction that lowers the energy using gradient descent. Think of it like rolling a ball down a hill defined by the energy landscape. You keep nudging it, step by step, until the energy stops changing much, meaning you've reached a low-energy valley, a good prediction. This process naturally allows for dynamic computation, facet 1, because you can decide how many steps to take. And importantly, the energy score itself tells you how good the prediction is, giving you a measure of uncertainty, facet 2, and acting as a verifier, facet 3. Now, why focus on verification? This isn't just some academic quirk, it's rooted in computer science theory. There's a fundamental asymmetry. Verifying a solution is often way easier than finding one. Think about a maze. If someone gives you a path and says, "This solves the maze," you can quickly check each step. But finding that path from scratch? That's the hard part. EBMs leverage this. Instead of learning to generate the path directly, they learn the rulebook for checking if a path is valid. The generation process then becomes simply following the rules to find the lowest energy state. This has huge implications for generalization. A model trained to solve mazes might get stuck on a slightly different maze layout. But a model trained to verify paths? That skill transfers more easily. It's like knowing the rules of chess versus being able to play perfectly. This connects to something called the generative AI paradox. Many powerful models today are amazing at making things, but terrible at judging whether those things make sense. They can't assess their own work. EBMs, by design, learn to judge, to verify. This built-in discrimination skill is a major advantage. Okay, the verification idea is cool, but how do you actually train these EBMs efficiently, especially for massive datasets and complex problems? Traditional methods run into trouble with the curse of dimensionality. Imagine trying to find a needle in a haystack. As the haystack gets bigger, the number of places you need to check explodes. Contrastive methods, which try to push good examples closer and bad examples further away, suffer badly here. So, the researchers took a different route. They framed the training itself as an optimization problem. The goal is to shape the energy landscape so that the correct answers lie in nice, low-energy valleys. During training for each input x, they start with a random prediction y hat 0. Then, they perform several steps of gradient descent, just like during inference, to try and find the minimum energy prediction. After these steps, they calculate the actual loss, like cross-entropy for text or mean-squared error for images. Crucially, they backpropagate this loss all the way back through the entire optimization process. This means the model learns not just to make a good final prediction, but also how to effectively navigate the energy landscape to get there. It's a bit like teaching a student not just the answer, but also the best way to approach the problem. Training this way is scalable, but getting smooth, well-behaved energy landscapes, especially in the complex, high-dimensional spaces we deal with in real-world data, is still tough. Imagine trying to roll a ball down a very bumpy, uneven hill. It might get stuck in a small dip, or take a long time to reach the bottom. To tame this, the researchers developed some clever regularization techniques. First, they used a replay buffer. This stores the successful optimization paths taken during training, helping the model learn the shape of the landscape near the good solutions. Second, they added Langevin dynamics. This is basically adding a bit of random noise to the gradient updates. Think of it as giving the ball a little wiggle, encouraging it to explore different paths and escape shallow local minima, leading to a more globally optimal solution. Finally, they randomized the step size and the number of optimization steps during training. This prevents the model from learning any single path too well and forces it to be robust to different ways of reaching the solution. Together, these tricks help create smoother, more convex energy landscapes, which are essential for reliable and efficient thinking. Now, how do you implement these ideas using the powerful transformer architecture? Transformers are great because they handle parallel processing, are stable, and scale well, which is exactly what EBMs need. So, the researchers built two main versions of energy-based transformers. First, a decoder-only version inspired by the famous GPT models. This one predicts sequences step by step, like predicting the next word in a sentence. It's autoregressive. Implementing this correctly is tricky because you need to ensure the model doesn't cheat by looking ahead at future tokens, a common pitfall in sequence modeling. Second, they built a bidirectional version. This allows the model to look at the entire sequence at once, like BERT or D, which is useful for tasks like image denoising where you need context from all parts of the image. These architectures provide the necessary building blocks to apply the EBM principles to both discrete text and continuous visual data. Theory is nice, but does it work? The researchers put their EBTs through rigorous testing. They looked at two main types of tasks. For discrete data, like text, they used autoregressive language modeling, the classic task of predicting the next word. For continuous data, like video or images, they tackled video frame prediction, predicting the next frame in a video, and image denoising, cleaning up noisy images. For comparison, they used the standard transformer Jaja recipe for language and the diffusion transformer, DIT, for vision tasks. Importantly, since EBTs are a fundamentally different architecture, they couldn't just fine-tune existing models, they had to train everything from scratch. They measured performance in two key ways. First, learning scalability. How quickly does the model improve as you increase resources like more data, larger batches, more parameters, or more compute? Second, thinking scalability. How much does performance improve when you allow the model to think longer during inference, measured by the number of optimization steps, NFEs? Finally, they checked generalization. How well do these models perform on tasks they weren't specifically trained on, especially data that looks different from the training data, OOD? Let's look at the results for language first. They compared EBTs against the standard transformer Jaja model on a massive text corpus, Red Pajama v2. They measured how performance improved as they scaled up various aspects: the amount of data, the batch size, the model depth, the total number of parameters, the computational cost measured in flops, and the embedding dimension width. The results were striking. Across all these dimensions, EBTs consistently showed a higher scaling rate. Look at Figure 5, showing parameters, flops, and embedding dimension. The blue lines for EBTs are consistently above the orange lines for transformer Jaja. This means EBTs learned faster and achieved better performance with the same amount of resources. They found scaling rates up to 35% higher. This suggests EBTs are inherently more efficient learners, needing less data or compute to reach the same level of performance. This is a huge deal, especially considering the cost of training large models. To our knowledge, this is the first time a model has been shown to outscale the standard transformer Jaja recipe across multiple axes without using a special tokenizer. Okay, so EBTs learn faster. But what about their thinking capabilities? Table 2 shows an ablation study confirming that those regularization techniques we talked about, replay buffer, Langevin noise, randomizing steps, are essential for getting good results from the thinking process. Now, Figure 6a is fascinating. It shows how performance changes on challenging, out-of-distribution data as you increase the number of optimization steps during inference. For the standard transformer Jaja, the line is flat, no improvement. But for EBTs, the more steps you take, the better they get, reducing perplexity by up to 29%. This demonstrates the dynamic computation facet in action. Figure 6b shows self-verification. Here, they generate multiple predictions and pick the one with the lowest energy. Again, EBTs benefit significantly, and interestingly, the benefit grows as the model gets bigger and trained on more data. Figure 8 visualizes this uncertainty modeling. Notice how simple words like the or but quickly settle to low energy, indicating low uncertainty. Harder words like fox or problem take longer to converge and have higher energy, reflecting the model's uncertainty. This confirms the model is learning to express uncertainty naturally. Does this thinking actually help the model generalize to new unseen situations? Figure 7 plots performance on different datasets ranked by how different they are from the training data. The x-axis shows the OOD shift. What we see is a clear trend. The bigger the gap between the test data and the training data, the more the thinking process helps EBTs. This strongly suggests that System 2 thinking is crucial for tackling novel challenges. Table 3 compares overall performance on various downstream tasks. Interestingly, in some cases, the EBT models had slightly worse perplexity during pre-training compared to the transformer Jaja models. However, on the downstream tasks, especially the harder ones, EBTs often performed better. This indicates that EBTs generalize better, even if they don't achieve the absolute best score during initial training. This combination of better learning scalability and superior generalization, particularly to OOD data, points towards a significant advantage for EBTs, especially when scaled up to the size of modern foundation models. Now, let's switch gears to continuous data, specifically video. They trained models to predict the next frame in a video sequence using the something something v2 dataset. Unlike the text experiments, video datasets are often smaller, so the models get trained on the same data repeatedly. This tests how well the model can fit the data. Again, EBTs showed superior scaling. Look at Figure 9. While they might start with a slightly higher loss, the rate at which they improve is significantly faster, over 33% higher scaling rate for both embedding dimension and non-embedding parameters. Why might this be? The authors suggest it's because EBTs, with their energy-based approach, can naturally handle uncertainty in continuous spaces like video frames, unlike standard transformers which often need workarounds like discretization. Figure 11 beautifully illustrates this. It shows the energy assigned to predicted frames in a video. Early frames, where the scene is unclear, have high energy. As the main object appears, the energy drops, indicating lower uncertainty. The model learns this without explicit supervision, just by minimizing the loss. Finally, they tested the bidirectional EBTs on image denoising, a task where diffusion models like DIT are strong. They trained the EBTs using a similar noise schedule to diffusion models. The results were impressive. Table 4 shows that EBTs significantly outperform DIT on both standard and more challenging, out-of-distribution noisy images measured by PSNR and MSE. But here's the kicker: they achieved this better quality using dramatically fewer forward passes, about 1% of what DIT needs. Figure 12 shows this clearly. The EBT line reaches higher PSNR much faster with fewer steps. This is a huge efficiency gain. Furthermore, when they tested the learned representations on a standard image classification task, ImageNet-1ec, EBTs achieved about 10 times higher accuracy than DIT. This suggests that the representations learned by EBTs during denoising capture much richer visual features. It hints that EBTs might lead to generative models that not only produce better images but also understand them better. So, what's the big picture here? The energy-based transformers present a compelling new way to build AI. They offer significantly better learning scalability, meaning they learn faster and more efficiently, which is crucial as data becomes scarcer and models grow larger. Their built-in System 2 thinking, enabled by the energy-based framework, provides substantial performance boosts, especially when tackling difficult or unseen data. This thinking capability seems to be key to their improved generalization. They also naturally handle uncertainty in continuous data, a feature often lacking in standard models. And the bidirectional version shows great promise for tasks like image generation, potentially leading to models that are not only better at creating things, but also better at understanding them. The core idea of learning to verify rather than just predict seems to be central to these advantages. In summary, energy-based transformers represent a promising step forward. By framing prediction as an optimization problem guided by a learned verifier, they enable unsupervised System 2 thinking. This approach leads to models that learn more efficiently, think more effectively, and generalize better, particularly when faced with the unknown. It's a fascinating new direction for building more capable and adaptable AI systems.